All right, everyone is in and the recording is started.
Great. Well, welcome everybody. Thank you for joining us for this edition of our UW-Madison-CBE town hall meeting. I hope to share with you some updates on various aspects of the department over the next few minutes. Thank you also for the questions that you added in during registration. I'll try to hit on some of those high points as I go through the slides today. And then we have a very special guest today to share some of his research with you, Professor Marcel Schreier, and he'll come in after I give the updates. So hopefully that'll be a really exciting look into some of the cutting edge research that's going on in the department. So just like to start with some faculty news. The first news item is to remind those of you who have joined us before, or perhaps new information for those joining us for the first time. We're really excited to have two new faculty members starting in just a couple of weeks. In fact, I saw Whitney walking around the hallway yesterday, so it was great to see them on campus already. So the two new hires are Dr. Whitney Liu. So she's largely in the soft matter design of materials space, so we'll bring a really critical element to our department. And the second is Dr. Rosie Sersansky, who's more on the modeling side of materials and really working at how materials assemble and form building blocks for functional materials. I should also point out that that'll bring us up to 20 faculty, which is the highest number that we've had since I've been here at UW-Madison. And I'll also point out here down in the bottom that we have actually 3 more open positions. In fact, I just came from a faculty search meeting, so we have a lot of great candidates, and we're undergoing that process of trying to fill those 3 open positions. I should also note that as you grow the faculty and have a vibrant faculty, this also goes along with growth in the graduate student population, the staff needed to manage all of the new grant funding coming in, and so on. And so some of you may have seen some of the goings on out in California with the graduate students and postdocs, working to get equitable wages and things. And, what we for sure focus on here at UW-Madison is making sure that all of our graduate students, faculty, and staff are really competitively compensated. So that helps us bring people in, bring new recruits in, whether at the faculty or the student levels, and again, have a unified department. So just a couple of new awards that I'd like to focus on. So we have a lot of awards I could talk about, but I really wanted to emphasize how great our semi-new faculty are doing. So 2 of our assistant professors now in their 3rd year here on campus won major national awards. So Matt Gebbe was the recipient of an Army Research Office Early Career Award. And this is dealing with liquid electrolytes for battery technology. Marcel Schreier, who's going to be our guest speaker today, was the recipient of a Beckman Young Investigator and Packard Fellowship. So these are 2 different awards that are highly competitive as well, national awards. And Marcel will be telling us much more about his work today, but this generally in the space of working with electrocatalysis to transform chemicals and fuels. So one of the events I'd like to emphasize today is our recent College of Engineering Engineers Day. This is where different alums of the college are recognized for their early career or entire career accomplishments. And the Chemical and Biological Engineering Department was fortunate to have 2 awardees this year chosen. One is David Hemker, who received the Distinguished Achievement Award. This is a picture here of Dave giving his acceptance speech at that Engineers Day evening event. So Dave was a bachelor's graduate in 1984, and then went on to the Silicon Valley space and was working at various companies before he retired as the chief technology officer at Lam Research Corporation. And here I just have his award citation that Dave is a chemical engineer and technology leader whose numerous innovations have advanced semiconductor processing and thin film applications. So it's great to have Dave and his mom and his family here on campus, and even decided to go to the football game against Maryland the next day. And I saw him soaking in the rain and wind. And so I said, that must be a dedicated alum right there. Kevin Ittrey was the Early Career Achievement Award winner. So Kevin was actually in one of my first mass transfer operations courses. So I got to know him then. He's president at Grace Matthews, graduated here with a bachelor's in 2003. And his citation was that he's a chemical engineer and business leader who has improved chemical industry production operations and has successfully managed national and international company mergers and acquisitions. And so Kevin was our Early Career Achievement Award. And I'd like to dovetail that a little bit into undergraduate news, because one of the great things is when we have these distinguished alums coming on campus, they have the opportunity to meet with faculty, staff, and students. And one of those events is an undergraduate scholarship reception. So we have, as noted here, about 550 undergraduates currently in the program. About 37% of those are female and 7% are unrepresented minority students. And I would say, like to tell you that in the College of Engineering, these are both near the top in terms of how we have diversified our undergraduate population. In terms of the scholarship reception, a lot of these students, of these 550, 80 to 90 of those each year receive support from the department. And that support comes through endowed scholarship funds. So this past year was about $300,000 that was given to support undergraduate scholarships. And it really helps people get through the program and leave the program without having any debt. And here I just have a couple of pictures of the students at the scholarship reception. I would say of those 80 to 90 students, about 2/3 of them showed up for the scholarship reception. And this was a roundtable discussion with our distinguished award winners, Dave Hemker and Kevin Ittrey. And basically we had to drag Dave and Kevin away at the end of this because the students had so many questions for them about their careers and how they applied their chemical engineering degrees towards their ultimate careers. One graduate student news note here. I just wanted to point out some of the other things that the department graduate students are doing that is a little bit of beyond the norm of coming in to do their research work and publishing. And this is a graduate student who's in her 4th year, Liz Appelt. She's actually a graduate student in my laboratory. And she was recognized by the World Health Organization for contributing to the development of a COVID vaccine in Africa. So in the continent of Africa, there's a company called Afrigen, which was the first company dealing with biologics and vaccine development. And as part of her training, Liz is an awardee to the National Institutes of Health Biotechnology Training Program. And that mandates that they go and do an internship at some point during the graduate career. So this summer, she went to South Africa to work with Afrigen and really helped bring their analytical processes for GMP manufacturing up to par so they could do the equivalent of what would be FDA filings here in the United States. And I'll point out that Liz, before she started with us, had 5 years in the biotech industry. So she really brought really advanced skills to bear to help this developing continent in terms of bringing a vaccine to bear for COVID-19. So update a little bit on the physical infrastructure. I know some of you on the call here already know that we're actively renovating some major spaces in Engineering Hall in the Department of Chemical and Biological Engineering. And we're doing both the instructional space, which a lot of us affectionately know, instructional laboratory space, which a lot of us affectionately know as summer lab space, which is in the basement, and also a major biolaboratory renovation on the 3rd floor of Engineering Hall. So I'd really like to announce that construction started just a few weeks ago, and I can tell you that right now, and for the past week, my chair in this office has been vibrating because they've been jackhammering the floor out of the old summer lab. So luckily, the civil engineering is on the other side of the building up over the summer lab. They have a lot of complaints. We're distal from that, and we're still getting those vibrations as they tear the floor up. But what's really exciting is once this construction started, so there's going to be substantially completed summer, fall of 2023. So it'll take just a little, about a year basically to finish both of these major projects. And I just wanted to point out that we'll be launching an all-call for support to finish off these renovations. I'll just point out that there are naming options still available, and that all the donors will be recognized in some way in the new space. So if this strikes a chord with you and you're interested in learning more about this, please feel free to contact Mike Holland, who's one of the development experts here in the Department of Chemical and Biological Engineering. What I'd like to show and elaborate on is this picture that I have here. This is the architect's rendering of what the space will look like when it's done. And what you're looking at here is if you came off of Camp Randall side of Engineering Hall and entered the basement, on the left where you see the crest here, the W crest, that's the old summer lab space, okay? And on the right, where it's a little bit red here, is new space that we acquired in the past couple of years that's going to become the pilot plant space. So I just wanted to show you a couple pictorial updates of this process. Here's the classical summer lab space. So the rendering up above is what it's going to look like. The panoramic picture on the bottom is what that summer lab space looked like about a week and a half ago. So this was before they started taking the floor out. And you can see all the benches, everything is out of there. And hopefully you can see the columns and you can envision what this space is going to look like. You'll also notice up here in this top rendering that there are windows up there. So if you were like me and went through summer lab here at UW-Madison, you will not remember having natural light down there. But there are windows down there because it's 1.5 stories tall, and those windows will be punched out and expanded so that we have some nice natural light, despite the fact that the laboratories are in the basement. The second space I'd like to show you a picture of is this newer space, or this pilot plant space. And so hopefully you see on the top the artist's rendering or the architect's rendering of that space. What's really neat, you'll notice it goes down. This is a full 2-story space that's going to allow us to put larger process equipment directly in this space. So that's why we're sort of calling it the pilot plant space. And we're integrating the technology then to almost operate this as a pilot plant. And the vision is really to have a control room that's off of the pilot plant space for monitoring and control of this new equipment. So we're always trying to bring technology into the program. And this is one that we can bring in some industrial technology. In the bottom panel here, hopefully you can see that this is what it looks like now. You can see that it is a tall space. What they're basically going to be doing is taking the floor out of here and actually going down another 3 or 4 feet to get that full 2 stories. So this is a huge addition actually to our instructional laboratory space. So with that, I will now transition to introducing Marcel, who's going to join us to tell us a little bit about his research. So Marcel did his master's degree in chemical and bioengineering at ETH Zurich. So you'll notice in Switzerland. He then proceeded to get his PhD in chemistry at another Swiss institute, EPFL, and has then followed that with a postdoctoral researcher stint at MIT. And he joined us in 2020 as the Richard H. Soet Assistant Professor. And I'll point out that today it really snowed for the first time here in Madison. And I know Marcel is a big fan of snow in the Swiss mountains. We're not quite in the mountains here, Marcel, but hopefully it makes you feel a little bit at home today as you walked into the building. But with that, I'll turn it over to Marcel, and I will just ask that if you have questions for Marcel, you can save them to the end of his presentation. We'll leave a couple minutes or type them into the chat box. So with that, Marcel, I'll stop sharing and you can share your slides.
Thank you very much. So you took my joke that I had nicely prepared about the snow and how much it feels like home. So indeed, that is the correct interpretation. So yeah, I'm going to get started. I have 15 minutes. I have a great desire to share stuff. So I have a lot of slides. I will have to skip some of them, I have a feeling. But so my name is Marcel Schreier. I'm from Switzerland. So you can hear this from my accent. And so I came here pretty much exactly a year, 2 years ago on campus. And I want to talk a little bit about what my group is doing. We're working on electrocatalysis for energy storage, as well as rendering chemical synthesis more sustainable. So let's first go into the background. So why am I excited about this hot topic of electrocatalysis? Well, we have, as you can see in this picture, more and more sustainable electrical sources coming online, mostly from wind and solar power. And it is therefore not surprising that the cost of renewable electricity is rapidly decreasing. So you can see that from 2010 to 2018, solar electricity average cost went from 37 cents per kilowatt hour to 9 cents per kilowatt hour. So this is a precipitous cost, which drops right into the cost range of some fossil fuels. And so now we are in that situation where we essentially start to have a sustainable energy source that just starts about to be cost competitive with fossil resources. Now this opens opportunities. When we look at the chemical and petrochemical industry around us, we can see that the industry that makes and transforms the plastics and that makes and converts the fuels that we are using can be depicted in sort of a cycle. One part of this cycle is the synthesis of chemical building blocks from CO2 and water. The second part is the transformation of these building blocks into chemicals which have beneficial properties, either as plastics or as fuels. And then eventually we have the step where we extract the chemical energy that is stored in these bonds through combustion and make chemicals do useful work. Currently, our entire energy system entirely exchanges energy with chemical transformations in the form of heat. And this has sustainability disadvantages because everything is driven by burning fossil fuels. We are burning fossil fuels for transport, to drive our cars. We are burning fossil fuels to make and transform plastics. Even plastics recycling is driven by fossil energy. So if we want to be really sustainable, we need to think, well, how can we get rid of these fossil driving forces and instead replace them with this increasingly abundant sustainable energy and build a chemical industry, a chemical and fuels industry, where this entire cycle exchanges energy no longer with heat, but directly with electricity. That's what my group works on. We see an opportunity to use renewable electricity to power a sustainable chemical industry. The question then is, how do we tackle this problem? How do we use renewable electricity to make chemical reactions happen? And the key to this is understanding and controlling electrocatalytic reactivity. So I'm going to, in the following few minutes, walk you through some examples how we understand and control electrocatalytic reactivity and convince electricity to do the chemical reactions we want it to do. Going back to this drawing, I'm first going to talk here, what is marked in red, the transformation of carbon dioxide to chemicals and fuels. This is what I did a lot of in my PhD and postdoc work. I'm going to show you how all the stuff that we can learn from these reactions that allow us to electrically take CO2 back into fuels, how all the insight we gain from there allows us to expand the reaction scope, so the reactivity of what electrocatalysis can do, to really complex valorization reactions. And thereby allows us to kind of step by step work through the chemical and petrochemical value chain and replace fossil driving forces with sustainable electricity. Now, to be able to explain what we are doing, I need to first introduce how an electrocatalytic reaction works in the first place. So here we have a very simple example. This is actually from a paper of mine as a grad student. We're taking carbon dioxide and we're transforming it to carbon monoxide. That's really the simplest carbon dioxide valorization step. CO2 comes into the cell, and then we start applying a voltage between two electrodes, between iridium oxide and gold. On the iridium oxide, the voltage does an interesting reaction. It rips electrons out of water and thereby generates oxygen. We then take the electrons that we pulled out, we push them to the other side of the cell, push them into a gold electrode, where these electrons react with CO2, form CO and water. And so we are able to use electricity to transform carbon dioxide to carbon monoxide. What really makes the magic happen here is the dynamics that occur at electrochemical interfaces. These interfaces are generated when an electrode comes into contact with an electrolyte, very often a liquid. What then happens is that ions in the solution rearrange, they generate an electrical field, and this electrical field interacts with chemical species and then allows us to drive really complex sequences of chemical events, which allows us to do chemical transformations. So in my PhD and postdoc, I worked on understanding and controlling the reactivity at the interface between an electrode and an electrolyte that allows us to transform carbon dioxide. When we take CO2, we can actually transform it to CO, but we're even able to make really complex hydrocarbons such as ethylene and methane. And what I cared about as a graduate student and as a postdoc was understanding how these processes work and how we can control them. And I'm going to go now almost chronologically through some of the things I have learned, and will then show you how it influences what my group is doing here at the University of Wisconsin. I'm going to show you how we can use different elements of the electrochemical interface to control the reaction rate and the reaction outcome. First, let's see how we can control the electrolyte in order to influence how an electrochemical reaction occurs. The problem with electrochemical reactions as they stand is that they often use a lot of energy. And everything we want to do is decrease the activation barriers that the reaction have to go through. So here we are looking at an example where we have a silver electrode that is exposed to an electrolyte. When we introduce carbon dioxide into this system and we apply a voltage to the electrode, and we scan the voltage, we can see that at some point we start to observe a negative current here. And this current corresponds again to carbon monoxide formation. So we're able to use electricity to transform CO2 to CO. But we need to invest a lot of voltage, a lot of energy in order to get this reaction going. We can control the rate of this reaction by modifying the properties of the electrolyte. So what we did is we introduced an ionic liquid, and just as a small amount as a dopant. And when we did that, we were able to substantially decrease the driving force that is used in order to get this reaction going. We then did quite involved structure activity correlation measurements, and we found that very likely the reason why we are able to decrease the activation barrier of this reaction by adding molecular additives is because they are specifically interacting with certain steps in the electrochemical reaction. For example, we know that the rate limiting step of the electrochemical transformation of CO2 to CO is the adsorption of CO2 to the surface. This leads to a negatively charged intermediate. And our research has shown at that time that very likely the structure of imidazonium cations is able to stabilize the transition state as well as the intermediates that are formed and thereby enhance the reaction rate. So this is an example how we can tune properties of the electrolyte, so species that are present in an electrolyte, to control the outcome of an electrochemical reaction. But an electrochemical interface does not only have an electrolyte, it also has an electrode. Obviously, we also can control the outcome of the reaction by controlling electrode properties. So, one catalyst that we can use for transforming carbon dioxide is copper. Copper is a really cool catalyst because it can make everything. It makes carbon monoxide, it makes ethylene, it makes methane, it makes ethanol, it makes propanol. So we can make a whole host of important chemicals from CO2 using electricity when we use copper. The big problem, however, is that copper makes everything at once. And no one has really figured out how to control the selectivity. So how can we influence this selectivity? I cannot go through the whole story, but serendipitously, I found that when you take a completely non-selective copper material and you measure its performance, you can see that we make very little desired products. So carbon monoxide is almost not produced, whereas hydrogen, that is a product that we don't want to produce at all, is fairly dominant. When I coated this electrode with very thin monolayers of tin, I was able to suddenly see a strong production of carbon monoxide and completely suppress hydrogen generation, which is what we do not want. So we are able to take a material that makes everything. We put two monolayers of tin on top, and we're able to completely change the selectivity profile from something that makes hydrogen, which we do not want, to a material that makes almost only desired carbon monoxide. And this is achieved due to the fact that adding tin modifies the surface, decreases the binding strength both of hydrogen intermediates and carbon monoxide intermediates, and thereby drives us into the desired reaction, enhancing CO2 reduction activity and suppressing the undesired activity for hydrogen generation. So this shows you how we can play on properties of the electrolyte and the electrode material to control the outcome of the transformation of CO2 to CO. This is this first cycle of the reaction. But this reaction can go beyond that. We can actually take CO and transform it to hydrocarbon compounds. This goes through very complex catalytic reactions, and we don't know how they work. So in one project, we developed model systems, non-aqueous model systems that allow us to study the outcome of these reactions using kinetics. So here we are working at minus 35 degrees Celsius doing electrocatalysis and measuring reaction rates. When we do that, we get extremely clean kinetic data on the production of hydrocarbons, in this case, methane. And here are some really interesting findings. When we use electrochemical kinetics to analyze the pathway through which methane is formed, we can actually extract what is called a transfer coefficient. Very happy to explain how this comes about, but it will need a little bit of time, so I'm not going to do it right now. But when we measure the transfer coefficient for methane generation, we find that it is 1. And that tells us that at the point where we reach the rate limiting step of the reaction, we have already carried out all the electron transfers. So it tells us that in this electrocatalytic reaction, the rate limiting step is a chemical process, not an electrochemical process. So it's kind of surprising because we're doing electrocatalysis, but the kinetic data says, hey, the rate limiting step in your reaction is not an electron transfer. It is a chemical reaction, has nothing to do with electrochemistry. So when we then add to this additional kinetic information, So for example, we are changing the partial pressure of CO. We can find something that is also puzzling. As we increase the partial pressure of CO from 0.1 to 0.25 atmospheres, and then beyond this to 1 atmosphere, we can see that at a constant driving force here, we are decreasing the rate of methane production. And this is puzzling because CO is the substrate that leads to methane. So the more substrate we have, the less product we produce. How is this possible? Well, by really carefully analyzing the kinetics of this reaction, we were able to map out the reaction sequence that leads to methane production. And we could show that the rate limiting step of producing methane electrocatalytically is the surface reaction between a bound hydrogen and a bound carbon monoxide species to lead to a formate, formyl, and then down to hydrogenation to methane. This is a chemical reaction, not an electrochemical reaction. There's no, you see, there's no electron in here, no electron transfer. But still, the reaction rate depends on the electrochemical potential that we are applying. How is this possible? Well, the reason why this reaction is still controlled by electrochemistry is because the hydrogen atom that is involved in the hydrogenation step originates from an equilibrium between a proton donor in solution and the surface hydride. And this equilibrium is electrochemically controlled through the Nernst equation. So you can see that we can have reaction sequences where the rate limiting steps are thermocatalytic reactions, whereas only a subpart of the steps that are involved in catalysis are actually controlled by electrochemical potentials. So all of this gives us a little bit of a picture of how electrocatalysis works. And what my group does here at the University of Wisconsin is refine this picture, but also build on top of it. We are using the insight into electrocatalytic, fundamental electrocatalytic principles to open new reaction spaces. And here is our first publication that was published earlier this year in March 2020. It's from my student, Christine Lucky, the first student I got here. So what Christine was thinking is, we want to make chemicals that are more complex than what people can do with classic CO2 reduction. We want to make ethylene oxide. The reason why she wants to make ethylene oxide is because ethylene oxide is a very important precursor for plastics, but it is also very polluting. It is produced from ethylene in a fossil fuel-driven process over silver catalysts. And producing ethylene gives 1 ton of CO2 per ton of ethylene, whereas then taking ethylene to ethylene oxide releases an additional 0.9 tons of CO2 per ton of ethylene oxide. So it's a truly polluting chemical. And she wants to find a way to use sustainable energy and a sustainable substrate to get to ethylene oxide. In Wisconsin, we have a lot of ethanol, which we get from corn. So can we find a way to use electricity, renewable electricity, to go from ethanol to ethylene oxide? We can, and this is exactly what Christine did. She developed a pathway in which she uses chloride ions as catalysts to form 2-chloroethanol, which is then reacted with hydroxides to release the chloride ion again and generate ethylene oxide. This is quite an interesting reaction because it can use both sides of the electrochemical cell. On one side, in the oxidation, we form 2-chloroethanol. On the other side of the electrochemical cell, we are making hydrogen and we release hydroxide. When we then flow both sides of the electrochemical cell together, we have closed the cycle and we are able to take ethanol to ethylene oxide. Key to making this possible is figuring out a way to selectively transform ethanol to 2-chloroethanol. This is very hard. And I cannot go into the details now because we simply do not have time. I'm very happy to discuss more. So Christine used all our knowledge of interfacial engineering and reactivity, electrolyte properties, as well as homogeneous kinetics to trick nature into taking ethanol to 2-chloroethanol. And it worked. And she was able to build a cell that takes ethanol, uses only water, sodium chloride, and carbon electrodes to electrically transform this substrate to ethylene oxide. So we go from a truly polluting reaction to something that is resting on really benign environments to produce EO continuously over, in this case, an experiment of 2 hours. And here you can see the experimental setup. So this gives you a little bit of an overview of what we're doing. There's quite a few things I would love to share, but that are not completely ready for prime time. Some of them Worf doesn't let me talk about right now. But so we're taking this really to the next step. And so we've also, yeah, I cannot wait. We get another chance so that I can show you more of what we are doing. So we're really trying to get into there and open new reactivity pathways, understand what is going on, and really build the foundation for developing new energy storage and chemical synthesis technologies for an electricity-driven future. And the support that we are getting for this work is, as Eric has mentioned, the Beckman Foundation through the Beckman Young Investigator Award, from the David and Lucille Packard Foundation through the Packard Fellowship for Science and Engineering. There is support from ACSPRF, industry partners, so Enabling Technologies Consortium, which is out of the pharma industry, the Wisconsin MRSEC, WRF, and the NSF. And here are some impressions from my lab. My group is a real tinkerers, so we have a lot of circuits around and a lot of equipment. And I'm very happy to take any questions that you may have. I took this picture myself one evening on the way home from work.
So any questions, Kyle? Have you seen any questions, or are there any questions from the audience?
I haven't received any questions yet, Eric. Hi, everyone. This is Kyle Buckman. I work in the Alumni Relations and Development part of the department. As you have questions, feel free to type those in the chat, and Mike Holland and myself will moderate those and ask those of Marcel. Marcel, for those in the audience who didn't get a chance to hear about your arrival, would you just share, you've shared a lot of great research here, and as people type in their questions, just share a little bit about your journey and why you picked UW. You had lots of other universities that were interested. What stood out to UW for you?
Yeah, that's a really good question. And I'm just gonna go out with what's in my heart. What stood out was, yeah, I'm not gonna curate this too much. Look, when I came here, I interviewed at 11 universities, and UW stood out. I felt the conversations I had with the faculty were very much on the science. There was a lot of passion. People cared about the science less than about the mechanics of doing research. I felt that there was just more, it was pure. It was really a pure passion for science. And I felt that this was a very exciting environment. You know, conversations that stood out to me were with John In, with Victor Zavala, with George Huber, with Jim Dumesic. So these are really the conversations. And with Brian Flegger, who already showed me, here is your lab. But okay, so that stood out for this, but for different reason. But it's really like, you know, with John In, it was a deep conversation about kind of like how DNA came about. And you know, like I was blown away. Like nowhere else did I have like this depth of thought in conversations. With Victor Zavala, I was talking about optimizations and really complex system problems and how different parts of the economy and society and science interact with each other, and they take a systems view to all of this. And I love that. And with George Huber was like, well, he knew all the numbers for all the petrochemical processes, what is needed, what is not needed, kind of like, and I just felt that this was the real deal in terms of like just solid science. And that's what it really stood out already on the first interview.
That's great, Marcel. We did get a couple questions in the chat. Kyle, can you read those?
Yep. I'm just getting into those. So Marcel, there's a couple here that go into storage. So we'll start with, how does your work lead to energy storage capabilities? And we've got quite a few questions here, so maybe Reader's Digest version of answers for these.
Okay, so broadly, how does it lead into energy storage capabilities, right?
Yep.
Okay, so for the interest of time, I did not go into the whole detail as to how this relates to storage, but here is the quick answer. You know, when you have a fuel, okay, or like this one, okay, that's not really a fuel unless the refining didn't go like planned. But so you take this one and you transform the fuel to CO2 and water. This is a combustion reaction that releases energy. So if we take CO2 and water and generate the fuel, that is a reaction that requires an energy input to happen, right? Because the combustion is spontaneous. We can take a fuel, we react it with oxygen, we get CO2 and water, and we get a lot of energy out. You know, these alkanes, they are fantastic fuels. They're extremely energy dense. And so we use them as energy carriers in the form of gasoline. We burn them, we release energy. So the inverse is also true. If we make a fuel like gasoline, that requires that we provide an energy input. So if we take CO2 and water, use renewable electricity to transform CO2 and water to a hydrocarbon fuel, that means we have stored energy. And not only have we stored energy, but we have stored energy in an extremely energy dense energy carrier, which is much more energy dense than many other technologies, including batteries. And so this is really the attractive prospect there of doing energy storage in these fuels. Furthermore, fuels are really easy to transport. Once you have formed a liquid fuel, you just put it somewhere and then you wait until you need it. You put it on a truck, you transport it around. It is very energy dense. It is even easier to transport than electricity. And so this is how our work relates to energy storage. As soon as we take CO2 and water and make an alkane or an alcohol, that means we have stored tremendous amounts of energy in a very long-lived energy carrier. I hope this explains.
That's great, Marcel. Along those same lines, have you heard of sodium replacing lithium in batteries?
I have heard of sodium replacing lithium-ion batteries. I have. This is a whole area of kind of using alternative alkali metals. The reason for this is availability of these alkali metals, and it is an interesting technology. I have not formed an opinion about it to this point. It is not something that I am immediately at this stage working on. Originally, my training, so the very first interaction with electrochemistry I had was in battery research. I started 2009 as an intern at BASF, working on lithium-ion batteries and specifically on lithium-ion battery electrolytes. And so then I kind of like got exposure to this battery world. And the way I went into electrocatalysis was because I felt that I like this prospect of generating fuels. Because when you generate a fuel, you're no longer carrying around a lot of atoms just to store electrons on the material. So you don't need to carry the storage material, so that the whole technology around with you anymore. The only thing you're transporting is the fuel itself. And so I actually came from the battery area. I worked in battery also at ETH Zurich. There I did lithium sulfur batteries. And then I transitioned into electrocatalysis kind of with this desire to generate fuels.
Excellent. Thank you, Marcel. Question of scalability. What's the largest scale that this work that you presented has been demonstrated at?
I have an NDA. But what I can tell you is that we are asking questions about scalability, and it's super exciting. And I have a student who is really pouring a lot of effort into this question. I can comment a little bit about stuff that has been done publicly outside of our group. In my PhD, I worked with Siemens. My entire project was funded by Siemens. And Siemens was essentially working with us to take some of the CO2 reduction technology to larger scales. And they have taken it to substantial scales. There is also research groups and startup companies in the US and in Canada that have worked to scale up these CO2 reduction technologies. And what I can say is that work has been done in these directions. My personal sense it is not there yet, but my personal sense also is there is no reason that it shouldn't work. I think it is a question of how much we want it and how far we want to go. And my group, we have industry partners who are interested in specific sub areas of these technologies that I have discussed. And we get the chance, and I feel extremely lucky to get the chance to work with them on some scalability questions.
That's great, Marcel. With that scalability, you can solve some big problems. So one of the questions that we have is limited in what are the 2 to 3 really big problems that you think that this work can really solve over the next decade?
Okay, I think this is a multifaceted answer. So first of all, the work that I showed at the very end of the presentation, so our ethanol to ethylene oxide work, this work is really designed to use fundamental understanding of electrocatalysis to open new reaction pathways. This has a 10, 20-year horizon. What I want to do is I want to build the foundation that allows us to use electricity to do the reactions that humanity cares about. I just want to build this foundation on which we can then build a new a more sustainable chemical industry and a more sustainable energy economy. So there is a long-term horizon. Some other technologies, so the CO2 reduction technology, for example, to carbon monoxide, is close to commercialization. And that some partners, as well as some startup companies, are working on. So I do think that there are some immediate applications where we can actually do energy storage based on carbon dioxide reduction, but also based on other technologies that I have not discussed in this presentation, which is the generation of hydrogen that the US government is currently extremely interested in. These are much more near term. But I think that what we really try to do with the group is kind of like build this foundation so that we can build the ground on which we can put new future energy technologies and chemical synthesis technologies.
Thanks, Marcel. I think at that end of that question, I'd like to thank everybody for coming. If you have additional questions, feel free to reach out directly to Marcel. This is obviously a new growing area with a lot of our alums being in the petrochemical industry as well. So I'm sure your feedback would be welcome. Thank you again for attending, and we'll be in touch soon. Probably in 4 or 5 months for a spring town hall. So we hope to see you again. So thanks again and have a great rest of your week and weekend.
Thank you very much.